Well, good evening, everyone. Today's webinar is a deep reinforcement learning environment that everyone should be familiar with. It's one of the standard ones that we see a lot in this industry. It's taught, I think, in every. Just a second, I got a problem with my. I'm getting feedback here. Just a second. Just let me take a time out. I got to get a headset on so I'm not hearing myself in the speakers. Just a second. Okay, so that's a little better. Sorry about that. Seems like every time I do one of these webinars, I find something a little bit different that causes a problem. But as I said, today's webinar is going to be on deep reinforcement learning, and it's the taxi problem. And then, in addition to the standard taxi problem that you're probably all familiar with, we're also going to cover a new kind of deep reinforcement learning paradigm or method called MAXQ, and it's pretty interesting. So with that, let's go ahead and get started here. I'll share the slide deck again. Okay, so the taxi problem and MAXQ, hierarchical reinforcement learning, are the two big topics for today. So we'll start with the taxi environment. As I said, it's a very standard environment that you'll see in any deep reinforcement learning class. It consists of a state space that you see here in the picture. There's a taxi cab at some location in the state space. The space itself has 25 different squares. It looks like a little maze almost. It's a little neighborhood description as how it's kind of defined. The taxi that you see can move in one of four directions. It can go north, south, east, or west. But as you can see here, west has a red X on it. That indicates that it can't actually go west in this location because of this wall, this barrier that you see. So in addition to just the 25 squares, there's four of these squares that are unique and identified as R in the upper left corner, G upper right corner, B down here near the bottom, and lower left corner is Y. So those four locations are places where passengers could either be picked up or dropped off. And you see also on this diagram, there's two other little symbols. One of them has this little picture of I'm not sure what it is. I guess it's a picture of a person with a purple circle around him. That's where the passenger currently is waiting to be picked up. And then in the upper left corner at 00, you see this little marker, this blue marker that indicates where that passenger would like to go. So the objective of the agent in solving this environment is to navigate to the locations where the passengers are, perform an action to pick up the passenger, navigate to the destination location, and then perform an action to drop off the passenger there. So we kind of covered most of the information on this slide, but I just have another pictorial picture in the upper right corner here to show that same environment that we saw earlier, the state space. I think I mentioned the agent starts at a randomly chosen square. Maybe I didn't mention that, but random location to begin with. The passenger could be dropped off in the same location that it's picked up in. Actually, that's not a restriction to this particular environment. So you could pick them up in Y and then drop them off in Y and not have to navigate anywhere. That's a illegal action, actually. Okay, let's talk about actions and rewards. There's 6 primitive actions in this problem. I call them primitive actions here. If you just see this particular problem presented as a standalone problem, you might just see these as 6 actions. Here we call them primitive actions because later on when we talk about MAXQ, there's some higher level actions that are kind of in addition to these primitive actions that you see listed here. But in any case, we'll get to that in a second. The primitive actions include the navigation actions, either go north, east, south, or west, a pickup action, and a put down or drop off action. So those are the 6 things that the agent will be told by the environment, or the agent can tell the environment of actions to take. For rewards, there's a very common reward here. This first one is -1 every time an action is used. That's really common in these types of problems where you have like a maze type of a problem that you're facing, or in this case, a navigation problem. The reason that you're given -1 for every time you use an action is that you want to encourage the agent to make its way to the destination or to complete the problem as quickly as possible. So by having a -1 reward for every action you take, it encourages the agent to move smartly as quickly as it can figure out how to do to get from where it finds itself in the beginning to the solution state. If the agent successfully delivers a passenger, that means that there's a passenger on board the cab, it arrives at the correct destination and performs the put down action, then the agent receives 20 points reward. If the agent tries to pick up a passenger when the passenger doesn't exist in the square where the pickup action is put or taken, or it tries to put down or drop off a passenger at the wrong location, the agent is penalized with a reward of -10 for that action. I mentioned the walls and the barriers that you see, the walls surrounding the overall state space environment, and these extra barriers that are put in place. If the agent tries to direct the taxi to where it would hit one of these barriers, it won't pass through the barrier, but it also doesn't receive any additional penalty. It just gets the -1 penalty for taking an action. Otherwise, nothing else happens. It's just basically he's wasted a turn making that type of an action. So let me mention that lesson 10 in this course is the first mini project. If you haven't performed that project, I really encourage you to go take a look at it. It's a very simple project. It is this taxi cab project. The framework's been put together for you, and you can actually run the project by following the instructions that are in the mini project virtual environment, the workspace that's set up for you. And the goal in that mini project is to achieve a total reward of over 9.1, and it's not terribly difficult to do to get 9.1. The OpenAI gym environment that has a copy of this similar kind of project, that project would like you to get a reward of 9.7, and I'll have to say that could be a little bit difficult to achieve. I'd like to know if any of you were able to get to that high of a score. I performed this task and played with a few different values. I implemented a simple version of Q-learning where the action is just to return the best action you could take in a state, take the greedy action. I also experimented with putting around this action an epsilon greedy mechanism to take a random action with a certain probability and take the greedy action with 1 minus that probability. Surprisingly, I didn't actually get any better results with the epsilon greedy mechanism, but perhaps with other hyperparameter changes that should actually do better than a standard greedy action here. And then I just implemented the simple Q-learning. It's as you'll see in the textbook, it's a really simple algorithm. You just apply 1 minus an alpha variable and multiply that by the current state in action, and add on a delta. This is a TD delta kind of update where the value of the action in that state ends up getting the reward that's provided by the environment. plus a gamma. That's the discounted reward of the maximum of the actions you could have taken in the state. So real simple implementation. You could try some more complicated things here. You could try SARSA or other things. Experiment with what some of the things that you learn in the course and see how you do. It runs very quickly. You can run the 20,000 episodes that is set up to run in about 20 seconds. It doesn't take very long to experiment, try different things. See if you can beat my score, see if you can get a 9.7. It's a really good introduction to implementing these kinds of algorithms on the standard kinds of workspaces that Udacity has presented to you and that you'll see in the industry. So take a look at it. Okay, so that's the taxi problem in short. Now I'd like to introduce you to a new topic called MAXQ. It's one that's, I don't think it's actually covered in the textbook. It's something that's newer. I have to go back and look to see. I don't remember seeing it in the textbook. So I got this from a paper that was recommended by one of the Udacity teammates. So it's a paper by Thomas Dietrich et al. It's called Hierarchical Reinforcement Learning with the MAXQ Value Function Method. And I've given the URL here on archive if you'd like to download the paper and take a look at it. It's really more than just a paper. It's actually kind of a report of some of the work that they've done in their laboratory. I think it's in Stuttgart, Germany. That's where they work. And the paper is about 64 pages long, so it's kind of a little bit long, but it's got a lot of interesting topics in it. One of the topics that they cover is that they use the taxi problem that we just talked about as one of the examples for examining your algorithm, and it kind of has some interesting properties. So I thought it'd be a good thing to just talk about here in the context of this taxi environment. So the idea that they came up with is that the general agent learning algorithms that we've seen, sometimes they have a difficult time solving a problem that has a lot of different options in it. And in this case, the agent has to solve a problem for navigating to where a passenger is. It has to solve a problem for navigating to where a destination is. It's got to solve problems for putting down passengers, and sometimes trying to do all those things together with one state space description. The agent might have a difficult time learning all the things that it has to learn to be successful. So the idea that they have, and it's common, the actual idea itself is a common one, and that is to break up the problem into separate, smaller problems, and then kind of have agents working on each of those different smaller problems to, as a whole, solve the bigger problem. So what they've done is decomposed the main problem into these different subproblems, and then they decompose the value function into a set of value functions, one of them for each of the subproblems that are to be solved. And they introduced this term called recursive optimality. What they state in the paper is that their algorithm, this MAXQ algorithm, is not the optimal algorithm that could be found overall, but they do prove that it is recursively optimal, with the definition of recursive optimality being that the policy of each subtask is locally optimal given the policies of its children. So the children's subtasks are solving some subproblems. Given the state of those children tasks, every policy for each subtask is optimal with that context. So with that, let's take a look at the task graph. This is just the mechanism that the authors used to sort of describe the different tasks to be performed. Here you see a root task, a get task, a put task, pick up and put down as actions in those get and put tasks, and then a navigate task that you've seen the primitive actions for navigate already with north, south, east, and west. One little difference here is that if you look at navigate, navigate actually has this parameter t, and that can be one of two things. It can either be navigate to the source where a passenger is waiting to be picked up, or T could be a destination where you're navigating to the destination. And so that's just a parameter to the navigate task. And other than that, it doesn't know that it's a pickup spot or a drop-off spot. It's just told to navigate to that source or that destination location. So the authors of the paper then talk about these three different key kind of ideas that they talk about as why this algorithm kind of works better than just the standard algorithm that we just talked about earlier. One of these is an abstraction called temporal abstraction, and that is that navigating to a passenger's location can take a variable number of steps. So the navigate task you see there may be more than one primitive task. It could be a string of tasks, and it's not, sometimes it might be 1 or 2 steps, sometimes it might be 20 steps to accomplish that task. So once you enter that task, you stay in that task until that task ends. Each one of these are kind of like episodic, and then the temporal abstraction just states that you don't really know how long it's going to take when you get out of that task and you return to the higher level. That task completes, and you take a that action completes in the parent task. The second abstraction they talk about is a state abstraction, and this is probably the most powerful one, I think, of the mechanism. When, as an example, when you're solving the get passenger subtask, the destination doesn't matter because you're trying to get, find out where the passenger is and get the passenger. Likewise, similarly, the put passenger, it doesn't matter where the passenger started from. It only matters what the destination was. And then the second bullet here is probably even easier to understand, and that is that when you're navigating to a target location, it really doesn't matter whether the taxi cab is going there to pick up a passenger or it's navigating to that location to drop off a passenger. As far as navigate is concerned, it's just going to a location, location T that it's been told, and it doesn't really matter what its purpose is to get there. It just has to find a way to get there. So the last topic here is subtask sharing. This is a powerful mechanism because once you solve the navigation subtask once, like to navigate to the source, then that same task is shared with the deliver the passenger subtask. So there's a passenger on board. You use that same navigate task to navigate to the destination. And in this abstraction, the task of the agent is much simpler because it doesn't worry when it's navigating about picking up and putting and dropping off. It doesn't worry about whether it's traveling to or from a destination. It only knows that it's going to a particular place, and that's all it cares about. So it's a simpler. Each one of these are simpler problems to solve, and therefore you can get an agent to solve that environment in a simpler, more straightforward fashion. So we kind of talked about these subtasks. These are the subtasks they defined for their implementation of this hierarchical decomposition. The first one is navigate. Just move from the current location wherever the taxi finds itself and find its way to a specified target location. There's a get task, and that is kind of a higher level task. It includes moving from the current location to a passenger location, and then once you arrive there, to pick up the passenger. Likewise, there's kind of a high-level put task, and that is to move from the current location to the destination, and once you arrive at the destination, to drop off the passenger. And then the route task is the most important one, arguably, and that is the main task. So once you solve the route task, then your entire environment is solved, and the episode, the entire environment's complete, and you're done. So at that point, in the training environment, you will have solved an episode, and you move on at the new random starting location and start over, try to solve the new situation it finds itself in. So let's talk about the actions. Here we talk about 2 different types of actions. There's primitive actions, and then these high-level actions that were kind of created in the context of this hierarchical representation. The first actions are associated with the navigate task, and there's 4 primitive actions there: move north, south, east, and west. These are the same primitive actions that we saw earlier with the basic taxi cab problem. So for the get subtask, there's actually 2 actions that can be taken, and one of them is a primitive action, is to pick up a passenger. So pickup itself is one of the ones from the earlier task. But here we add a new task called navigate, and navigate is not a primitive action. It's an entire task. It's an entire subproblem to be solved. So that subtask is just an action in the context of the get subtask. And likewise, put has the primitive action drop off at passenger, and it also shares the navigate subtask, the same one that was used by the get subtask. And the root task just has 2 actions to it. They're both high-level tasks. There's no primitive tasks in this, no primitive actions in this root task. They're simply the get subtask and the put subtask. So it can either take an action to get a passenger, which means navigate to where the passenger is and pick him up, or a put subtask, which is navigate to where the passenger wants to be delivered and then drop him off. So with that, that's really what I want to talk about this evening. The context of the taxi cab problem itself. Again, I really encourage everyone to go and take a look at the mini project in lesson 10. Take your shot at that, see how well you can do. It's a good introduction to the big projects you'll accomplish. It's like a simple first step in that direction. It'll get you used to using the Udacity workspace and executing a problem in the workspace and checking out how well you can train an agent to perform this simple problem. And then we talked about the MAXQ value function decomposition. In summary, their idea is to break a bigger problem into smaller problems called subtasks, create new value functions for each subtask, and then have agents that are capable of being trained to solve those different subtasks. And I want to highlight just the subtask actions. They can either be primitive actions or they can be the child subtasks that are available to them based on the hierarchy that was established in laying out that function. So again, take a look at that paper. You can see some more details about how they actually implemented their algorithm and a lot of the theorems and things that they proved about the recursive optimality and other things. It's a very interesting read. So with that, we'll end the webinar. I didn't see anyone have a chat question, but we'll transition at this point to the Ask Me Anything session on Slack. So tune into Slack and feel free to ask questions about this webinar or anything else that you have a question on in the course, either about a project or just something that you'd like some clarification on in your reading. And with that, we'll see you next week. Bye.